Hi, welcome back to AP Physics 1. This is Unit 2, Dynamics. This is the big one, I would say, almost in this unit. This is kinetic and static friction, so this is topic 2.7. So there's a lot of little moving parts in this section. So up until this point, everything we made the assumption was that there was no friction involved in our problems. Now we're going to look at it what happens when we do have friction involved. Okay. So first, friction is the resistance that one surface or an object will encounter when moving against another. So friction only occurs when you have surfaces sliding on top of each other. Okay. Now there are two types of friction. The first one is kinetic friction, and this occurs when two surfaces in contact move relative to each other. One thing to note is that the friction is always opposite the direction of motion. And then the force of friction between the two surfaces does not depend on the surface area of contact. So a lot of times when you do a friction lab, they'll give you a block, and they may have you test, the big surface versus a small surface area. And ultimately what happens is students find out that, there's no difference between the friction of the big surface versus the small surface. The only thing that matters is that the two surfaces are interacting. As long as they have the same surface, they're going to have the same interaction with the friction. Okay. And then what happens is the magnitude of the friction, the kinetic friction, is going to be dependent on a value called the coefficient of kinetic friction. And so basically the coefficient of kinetic friction just basically tells you how slippery a surface is. Okay. The symbol for coefficient of friction is mu. And so the equation is going to be F sub K. In fact, a lot of times friction, it'll be written as a lowercase. So F sub K equals mu sub K times the normal force. Sorry, it looks like a W. But typically, the normal force is equal to the weight in some way. Okay? So if it's just a box sliding on the surface, it is just the weight. If it's on an inclined plane, it's going to be mg cosine theta. If you have any other kind of force acting on it, you may have to account for that. But that is the kinetic friction. And then the other type of friction that we have is static friction. And so static friction may occur between contacting surfaces of two objects that are not moving. So again, you see kinetic means moving, static means not moving. Okay, so basically static friction is the friction you have to overcome for an object to begin to move. Okay, whereas kinetic friction is now this is the friction of what happens when it is already moving. Okay, now static friction adopts the value and direction required to prevent an object from sliding on a surface. So it uses essentially the same equation, but it becomes an inequality versus it becoming an equality, right? And so what that means is whatever force you are exerting has to be greater than this, the product of the static coefficient and the normal force, okay? And the way, oftentimes if you're doing a lab, if you have, awesome devices, or it'll give you like friction or force versus time, not S. And you find that your graph will look something like this. It'll go up, and then it'll come down, right? And then it'll do something like this. So this first part, this is our static part. So the static part is linear. So anytime any force that is exerted from here to here, the object does not move. So no motion. And then this is our kinetic, which means once we break apart from that product right there, that's mu SFN. So once we break away from that value, then it drops down to be kinetic. Okay. And again, it's any point on that linear, right, that slope line portion, it will not move until you get to that coefficient times the normal force piece. Okay, and typically if you have the same two surfaces interacting, the coefficient of static friction is typically greater than the coefficient of kinetic friction of the pairs of surfaces. So that means if I have, this is often affecting when you have like tires, right? So rubber on road, right? Rubber on dry road, rubber on icy road, rubber on wet road. So the coefficient of static friction, the force it is to get the object to move, is going to be greater than when it gets to, the object is going to be moving. Okay. Now, these problems aren't hard in the sense of if you just follow, the problem solving process, the problems become easier, right? So, this process is very, intuitive. It, if you just follow it, draw the free body diagram, sum the forces in each direction, and then solve for what you're looking for. Okay, so let's look at an example problem using these concepts. All right, so it says here, you exert a force of 24 newtons sideways on an object and it accelerates from 0 to 12 meters per second over 5.2 meters. Okay, you know the coefficient of friction between the object and the ground is 0.58. So what is its mass? All right. So this has an added bonus. The first thing we have to do is figure out the acceleration. Well, we're going to use our cake, right, equations, our kinematics equations from unit 1 to determine that acceleration. So we're going to use v squared equals VO squared plus 2a delta x. Right? And then we're going to solve this equation for a. Well, that's going to be 0. And then all I have to do to find a is do v squared divided by 2 delta x. So it's final velocity squared divided by 2 times our displacement. So our final velocity is 12. And we're going to do 2 times 5.2 meters. And we get an acceleration of 13.8 meters per second squared. Okay, so that's step 1. I like to call these waterline questions because we've made this analogy to a duck on a pond. So this is the water line. So if I'm going from describing to what I'm doing is I'm going from describing what's happening to actually look at what's happening, right? So describing what that duck is doing by figuring out, okay, how much is this box being accelerated? And then taking that information and then going down below the water line to figure out, what is our mass of the object, okay? So now I may turn this into a force question, right? And so here's my free body diagram. So I got Fn and weight. So I have the normal force up, weight down. Those two are there if we have objects sliding. And then we have the the applied force, and then the frictional force. So I need to split this into 2 directions. Okay, and this is very typical of a friction problem. Your y direction is going to be the sum of the forces is going to be to y, and you have Fn minus Fg equals 0, which then says Fn equals Fg, which equals mg. Now I need this because I have friction on the other side. Prior to this, there would have been no friction. Okay, so now we need to do this because we need to figure out that normal force. And so we would do the sum of the forces in the x direction is ma, right? Because it tells us we accelerate it, which means we have a net force in the x direction. So we have applied force minus friction equals ma. And so I can do, let's plug in, not values, but let's plug in some, right, expression. So applied force minus friction, right? So mu Fn equals ma. But normal force was mg. Okay, so I'm just substituting in. So then I add mu mg to both sides. So I get Fa equals, I'm gonna do one step, or I'm gonna do 2 steps in one. So it's m. Both of them have a factor of m. So mu g plus a. Okay, and then finally do my final step of solving this for m. So I get applied force over mu g plus a. And so I have 24 divided by 0.58 times 10 plus our 13.8. I just apologize for all the wild areas where I'm at. So that tells us that the object has a mass of approximately 1.2 kilograms. Okay, and that makes sense because we're doing, we have a light object. We're accelerating at 13.8 meters per second squared. Okay, about mid-friction. Usually the coefficient goes between 0 and 1. And so we know this has to be a lighter object. Okay, but you could see the process. And I do want to point out, you see this mu g? That's the acceleration of a sliding object. So if we just push the box, right, our acceleration would be simply mu g. Okay. In fact, if we have a sliding car, right, if I jam on the brakes and my car becomes a sliding object, my acceleration would be negative mu g because I'm slowing down. Okay, we're getting near the end. So basically we have two topics left. We got spring forces and we have circular motion.